Bert, can you hear me?
Yes, I'm ready.
Okay, cool. So thanks for coming back. Our second speaker today is Professor Bertrand Halperin from Harvard University. He will give his second lecture focusing on the quantum Hall physics in Bilayer systems. So before we start, I want to note you that if you have any questions during the talk, please type them in the Q&A box located at the bottom of your Zoom window. Also, in the Q&A box, you can upvote questions that you think are particularly important. And at the end of the lecture, I will read out a few questions of the most popular questions to our speakers. Now, Bert, it's all your time.
Okay, hello. Am I coming through okay?
Yes, everything
yes, okay, good. Well, again, thank you for the introduction. Thank you for the summer school, which has been great so far. And there have been two great talks today. I'll do my best to add to them. What I want to talk about today follows up to some extent on what I talked about yesterday, but it's also closely related to some of the things that were discussed this morning by Professor Hu and by Professor Eisenstein this afternoon. It's called quantum Hall effects in two component systems. Last time I only talked about single component systems, and I have in mind both spin polarized bilayers. I'll say a little bit about that, and monolayers. In fact, I'll mostly be talking about spin polarized bilayers, and to some extent monolayers with spin. The outline is I'm going to review some general features of this of the two component systems, and then I'm going to talk quite a bit about systems with nu total equals 1, which is of course directly related to what we heard in the last talk. I'm going to talk a little bit about the excitation spectrum for a monolayer with spin at nu total equals 1. You heard some of that this morning, but I'll be following up a little bit on that. Mostly I'll be talking about spin polarized bilayers at nu total equals 1, again, to give a little bit more theory and a slightly different way of looking at things compared with what Jim just told you about. I will talk a little bit about experiments on double layer graphene, and then at the end, I hope I'll have time to talk about some quantum Hall states, quantized Hall states in bilayers with fractions not equal to 1, nu total different from 1, where you get a very different kind of combined fractional quantized Hall state. So just to remind you, we have the Hamiltonian for the two component systems I'm going to be looking at. We describe them in terms of each particle has a position, and we introduce a spin variable or pseudo spin variable, tau, which can be plus or minus 1. I is the labels the particle, and we have a Hamiltonian which has a kinetic energy part of the particles in the magnetic field, with some effective mass m, let us say. There'll be a Zeeman term which distinguishes between the two spin states, which might be 0, but we write it this way. Then there's an interaction, and the interaction we divide it into two parts. The interaction depends on just the position difference between the particles and also which layer they're in. And so I can write it as a u plus v times tau I tau j, such that u plus v is the interaction between electrons in the same layer, and u minus v would be the interaction between different electrons in different layers. I'm going to assume throughout here that there's no tunneling between the layers. I will focus on the situation where the cyclotron energy is large compared to the electron-electron interaction, so we can ignore mixing between Landau levels, and we're just interested in the various states within a given Landau level, typically the lowest one. And no tunneling between Landau levels. Again, Jim said that you can't get exactly 0, but it just needs to be completely negligible compared to other things for what I'm talking about, to be that way. compared with what was spoken about this morning, I should emphasize that when you talk about the experiments that we're talking about, the Bernoulli stacked graphene layers are totally not in this situation. In that situation, the tunneling between the two layers is extremely important, as she pointed out, but in the experiments I'm going to talk about, you have an insulator, a layer of HBN between the two graphene layers, perhaps 2 or 3 nanometers, and you can neglect the tunneling. Okay, so let's continue with this. Again, if I look at this and apply it to spins in a monolayer, we would expect that the interaction and the Coulomb interaction doesn't care about what the spins are. So in that case, the V term should be 0, which says that the interaction is the same between same spins and opposite spins. In that case, if I don't have EZ, this system actually has a full spin invariance. It doesn't care which spin axis I choose. So it has a full SU2 invariance. And it also applies to the bilayer system if I take the limit where the distance between the layers divided by the magnetic length goes to 0, again, then the Coulomb interaction, at least to a very large approximation, doesn't care which layer you're in. So again, you have essentially an SU2 invariance. But of course, as soon as you apply, have a finite separation, then you destroy the SU2 invariance. You still have a U1 invariance because to the extent that you have complete conservation of the number of electrons separately in each layer. That means, that is to say, there's no tunneling between them. The layer still has an invariance about rotations about the z-axis of this spin or pseudo-spin Tor. Okay, let me begin also by saying something about particle-hole symmetry in a partially full Landau level, which I didn't talk about in the single component system, but let me begin with that to remind you. So what we said that, again, in the limit of the mass going to 0, the cyclotron energy goes to infinity, and if we keep the electron and electron interactions fixed, then we neglect the mixing between Landau levels. And now if I have only one spin state occupied, and if there are only 2-body interactions, no 3-body interactions, for example, then there is, in fact, an exact particle-hole symmetry, which relates a state at a Landau level filling fraction nu rather, with a mapping onto states with 1 minus nu. And that's why you can so easily talk about holes in a filled Landau level, or electrons in an empty Landau level, or a certain density of holes, a certain density of electrons, and you can go back and forth between these descriptions. Now, mathematically, there also is, by the way, that this symmetry applies to the exact mapping between the energy differences between different states, excited states, ground state, and there are some other consequences for transport properties. Now, and I should emphasize that this particle-hole symmetry, it refers to systems which have different electron densities, so they have different filling fractions, but exactly the same magnetic field. In experiment, of course, you're often varying nu by varying the magnetic field, keeping the densities fixed. And in that case, you have to make some correction if you want to compare filling fraction nu and 1 minus nu. And again, although some Landau level mixing will be certainly present in any real system, a model with no Landau level mixing is generally a good starting point for discussions. A good theory should at least be able to describe that limit. And also experimentally, it seems that that in many cases, the Landau level mixing is surprisingly small, even if the cyclotron energy is not enormously big compared to the Coulomb interactions. And I should mention that, again, if for single layers, if you look at a Jane trial wave function, it is not precisely particle-hole symmetric. there's not an exact mapping between the trial wave function for, say, nu equals, for p equals, for positive and negative p's, which means between, say, something like 2/5 and 3/5. They wouldn't be exactly particle hole symmetric, and it's not exactly particle hole symmetric at filling fraction 1/2, but numerically they seem to be very close together, at least as far as one can tell by evaluating them in finite systems, which must be the case because, as I've already told you, they seem to work very well with the exact ground states, and the exact ground states have to be particle hole symmetric, obey these. And okay, and similarly, the predictions of the fermion-Chern-Simons theory, which I told you about last time, near filling fraction 1/2, they're not precisely particle hole symmetric in all aspects, but they are remarkably close, maybe even surprisingly close. And the exact reason for some differences between them is actually a matter of some consternation. We don't understand it completely, but it's not going to be relevant for what I talk about today. Okay, what about two-component systems? So, of course, with two-component systems, let's say if I have electrons with spin and I ignore the Zeeman splitting, then I have twofold degeneracy of the Landau levels. So a full Landau level requires not that F be an integer, but an even integer. And again, if there's no Landau level mixing, then a particle hole symmetry will then relate, if spins are fluctuating around, a particle hole state relates only a state with filling fraction F to a state with filling fraction 2 minus F. And in that case, of course, if I have F equals 1, I have precisely a half-filled Landau level, which is, of course, the situation we're going to be largely interested in. Now, depending on the filling fraction F and in other details, Coulomb energy may favor a state with both spin states partially occupied, as would be the case certainly for in the absence of any interactions, or it could be that exchange energy, the Coulomb energy, will favor spins to be maximally polarized. That means that's the ferromagnetism that we heard about, and it depends on filling fraction. If the Zeeman energy favors full polarization, then then it's ferromagnetic. Sorry, there's a mistake here. But if the Coulomb energy favors partial polarization or no polarization, then of course the Zeeman energy does favor full polarization. So if the Coulomb energy is in the other direction, there's a competition, and this can lead to a phase transition, as you say, as you increase the Zeeman field, keeping, say, the perpendicular field fixed but a varying parallel field, you can get phase transitions between a partially polarized state and a fully polarized state, or a completely unpolarized state and a fully polarized state. Now, in the case where, even because of Zeeman field or ferromagnetic interactions, it's fully polarized, that means that if F is less than 1, one state is going to be totally empty, and we could just ignore it, and we just have a partially filled Landau level with one component. And similarly, if F is greater than 1, one state is completely full and we can ignore it, and we have a partially polarized state with only one component, and then the symmetry is returned between F and 1 minus F, and between 1 plus F and 2 minus F, and also there's a symmetry now between F and 1 plus F. So all 4 states should have similar properties. Okay, so now that's very general. Let me specialize to the case of nu total equals 1. So electrons confined to a single Landau level in this limit, in a bilayer in the limit of d going to L, d over L be going to 0, or in a monolayer with spin at nu total equals 1, then this is the situation where we said the Hamiltonian has an exact SU2 symmetry, and it turns out that if you can neglect Landau level mixing, Hartree-Fock is exact in this state, and the Hartree-Fock requires it favors full polarization, so it requires it makes all the electrons have the same spin orientation, but this spin orientation can be anywhere on the Bloch sphere. So that means the ground state, we would say that all the electrons have the same value of this vector, pseudo-spin vector Tor, where Tor is a vector whose components are the 3 components of the the Pauli operators, tau x, tau y, and tau z. Tau z just measures the spin up or spin down, and tau x, tau y, of course, are the non-commuting perpendicular polarizations. And of course, if it's completely ferromagnetic and you have a Zeeman field in the z direction, the Zeeman field will, of course, immediately force all the electrons to line up with the magnetic field or opposite to the magnetic field, depending on the sign of the G factor. And so you get tau z equals plus or minus 1, and tau x equals tau y equals 0. So all the electrons have one spin or the other, or one layer or the other layer. But and in that case, we can talk about, in this SU2 symmetric case, we can look at what the excitons are, the excitations in that case. So let's say that all the electrons in the ground state have spin down, and then the lowest lying neutral excitations we can make are a bound state of an electron with spin up and a hole in the spin down Landau level. And this is an exciton. This was talked about in this morning's talk. It has a dispersion, which is shown on the right-hand side here. Basically, the exciton, the wave vector Q is good because it's a neutral object. And in the presence of a Zeeman field, in the limit of Q going to 0, you get a quadratic spectrum, which is basically a spin wave spectrum. It starts at the Zeeman frequency, and then it has a quadratic form of a quadratic form, which is Q squared LB squared times this EG, and I'm not sure what that lambda, I think should have been a pi, but I'm not sure what happened in there. But anyway, it's quadratic as Q goes to 0. And for large Q, instead it asymptotes to, at very large Q, it asymptotes to the Zeeman energy plus EG, where EG is the energy of an isolated electron and a hole very far away from each other. It's the energy gap, or the naive energy gap, if you don't have any extra for just a single quasi-particle, a single electron, a single hole, and that the energy difference is pi. It's given by pi over 2 to the 1/2 times this unit E squared over LB for pure Coulomb interactions, we can understand this because, as I've told you last time, and I think it was also mentioned this morning, when you have a neutral exciton of an bound state of an electron in a hole, the separation between, or the dipole moment, is just proportional to the wave vector Q, but it's perpendicular to it. And in fact, for electrons and holes, the separation between them is just Q times LB squared. And so what we see here is that there's a correction to the energy of the electron in the hole, which is due to the finite separation, and it's E squared over the separation for the Coulomb attraction. And that gives you this spectrum, which is quadratic at large distance, at small q, and becomes asymptotic to this at large q. Okay, and as was mentioned this morning, if the Zeeman energy is sufficiently small, the lowest energy charged excitations are not actually a bare electron, but they become these spin textures known as skyrmions for a finite value. That's in the limit of very small Zeeman energies. For reasonable values of the Zeeman energy, if it's small but not too small, the ground state turns out to be an electron bound to a single extra spin flipped or two extra spin flips, a small number of extra spin flips. They're often also referred to as skyrmions, though they're a little different in the sense that they preserve a rotational symmetry. Now, for the bilayer with D over LB not equal to 0, but not too large, Hartree-Fock is no longer exact, but it's still a very good approximation. And now the ground state can have electrons in both layers. In fact, it may be favored to have equal populations in the two layers when the layers are some intermediate distance apart. If the two layers are symmetric, then you're going to wind up with tau z not equal to plus or minus 1. But in the symmetric case, tau z would be equal to 0. And then since we were still required that the magnitude of tau vector be equal to 1, that means that tau x squared plus tau y squared must be greater than 0. And in fact, in the balance case, the expectation value of tau x squared plus the expectation value of tau y squared should be equal to 1. It doesn't matter because it still has U1 symmetry. We don't care where in the xy plane this points. So there's still a broken ground state. There's a broken symmetry in the ground state. The energy is independent of which way it points. There will be a Goldstone mode, as was mentioned this morning and this afternoon both, that corresponds to these fluctuations in this orientation. And this, of course, this is precisely an alternate description of this coherent bilayer integer quantized Wallace state that was described by Jim Eisenstein. Of course, the alternate description is in terms of a Bose condensation of excitons. If we start with a Philly-fold Landau spin up and down, let's say an empty spin up, and then I add bound states of electrons from one layer to the other, I'm adding these excitons, and the interlayer coherent state that we're talking about is a state as when the quantum, when the Bose condensate, when the excitons form a Bose condensate. The quantum phase of this Bose condensate, which is a free variable for it just corresponds to the orientation of the pseudospin in the xy plane in the magnetic description. And as again, there's deviations lead to a gapless Goldstone mode. In fact, that mode looks at large wave vectors. The mode will look, if the separation is small, what will happen here is just you'll get a very similar spectrum for large separations, but for small wave vectors, where the separation is small, this will become linear rather than quadratic. And it will start at 0. Here, it started at 0 just because the Zeeman energy wasn't included. But as was pointed out, even if you include Zeeman energy, if the polarization is in the perpendicular direction, then you get a 0 energy Goldstone mode. Okay, now questions. So one of the questions that you can ask is, what happens as you vary the ratio D over LB, of course, which, as we say, experiments are done by varying the magnetic field and the electron density, typically a fixed D. And we want to understand what happens. We know that at infinite separation, we have two independent layers, and we would like to know, can an interlayer coherent state, at least in principle, evolve continuously into the two separate layers for increasing D over LB, or must there be one or more phase transitions at some finite value of D over LB? And what happens at intermediate separations? So behavior at large separation. So theory now, I'm just talking about theory. So for two-layer separations, we believe that the ground state should have independent Fermi surfaces of these composite fermions. That's what we think the ground state looks like. At finite separations, if you have two matched Fermi surfaces, of course, any interaction between them could cause an attractive interaction, could cause or even any kind of interaction could cause instabilities to some type of BCS pairing. Depending on the type of interaction, you get BCS pairing of different symmetries, and that should occur. Perhaps it could be unstable for arbitrarily weak interactions, which means to say that the separated composite Fermi levels are not really a ground state for any finite separation. Now, there are many types of pairing. It turns out that one type of superconductivity, BCS type pairing, is if you let the pairing be in the channel of px plus ipy, momentum in the x direction plus I times momentum in the y direction, you get an exciton condensed state of these composite fermions, mind you, in the opposite layers, which turns out to have exactly the same symmetries and in principle can match smoothly onto the tightly bound fermion exciton condensate states that we've been talking about. And this, if this description is right, even if it's not correct at very large separations, it could still be useful for at intermediate separations. And I should say this work which was published in 2017 was very similar to work that was done earlier by Mueller, Simon, and Rizai in 2008, 2009. And they looked at trial wave functions based on Jane-type wave functions with introducing px plus ipy Cooper pairing between the composite fermions in different layers, and they compared what they found, the ground states that they found for these trial wave functions, with exact diagonalizations for finite system sizes, and they found reasonably good results for trial wave functions at intermediate separations, not so clear at small separations about what was happening. And I would just have to say that the system size were just too small to say much about large separations. It's just too hard. At large separations, the energy differences are very small, and the simulations of up to, say, 14 electrons on a sphere are not good enough to say what's going on. But nonetheless, if this px plus ipy pairing is correct, then you could have a situation in which with weak interactions, the energy gap delta just becomes smaller and smaller compared to EF. As in superconductivity, the pair size becomes larger and larger. Increasing separation causes delta to decrease until finally you get infinitely sized pairs, and you just have basically decoupled layers. On the other hand, decreasing separation should let delta become comparable to EF, then the pair size becomes comparable to the electron-electron spacing, and the state becomes equivalent to this a tightly bound interlayer coherent state, or a tightly bound exciton, a state of condensation of tightly bound excitons. And if this state is correct, then there could be a smooth transition as a function of separation. I'd like to introduce, however, an alternate description, which is, I think, a little easier in some ways to think about, and that's to take advantage of particle hole symmetry and make a particle hole transformation in one of the two layers. If it's equal, if the two layers are equal, it doesn't matter which one we transform in. If it's imbalanced, it's natural to put the electrons in the minority layer and the holes in the other layer, and we attach two flux quanta to each of these electrons in one layer and two flux quanta to the holes in the other layer, not to the electrons, but to the holes after we've made this transformation. Then at finite infinite separation, we have in one layer a Fermi surface of electron-like composite fermions. In the other one, we have a Fermi surface of hole-like composite fermions, but there still should be good descriptions of the ground state. Now, at finite separation, the natural thing to do would be to try to form an S wave, not P wave, but S wave BCS pairing between the electron-like composite fermions in one layer and the holes in the other. And it turns out, it's not at all obvious, but topologically, this is completely equivalent to the description of px plus ipy pairing between electrons in the two layers. And this has to do with the role of the gauge fields, which I won't go into, but they turn out to be topologically the same, but they are, of course, somewhat different trial wave functions. And they may help to understand what's going on, particularly in the limit where the layers get close together. In that limit, the pair radius becomes comparable to the distance between the pairs. The ground state that we would describe in this way is a Bose condensate, not of excitons so far, but of bound states of composite fermions. So they're electron and holes together with all this decoration from the gauge fields. So they're composite fermion excitons, whereas we know the true ground state should be real excitons. Well, that's okay, because once we get the tightly bound state of the electron composite fermion and the hole composite fermion, it actually becomes identical to a bound state of an electron and a hole, because all these Chern-Simons fields, they exert opposite forces on the electron and the hole. And since the electron and hole, if they're tightly bound together, it has no effect. So it makes no difference in that case, whether we're talking about electrons and holes or electron composite fermions and hole composite fermions. And Okay, so that means it more natural in that direction. And then, of course, it still works just as well at intermediate levels or large levels. You have, as the separation increases, you get sort of a small or a smooth crossover between something where you have tightly bound excitons and certainly where the exciton radius gets bigger, like in the BCS state. And recently, I've been involved in a project with Glenn Wagner, Dong Nguyen, and Steve Simon, where they, not I, but they, based on this wave function, we thought of some wave function, and they carried out numerical calculations, they constructed a Jane type trial wave function based on this S-wave BCS pairing of electron and hole composite fermions. They were able to evaluate it for up to 14 electrons on a sphere and found rather good overlaps. Here I just show you for 6 electrons in each layer. So it's 12 electrons altogether. And this axis, which I'm not sure how well it showed, this is D over LB on a sphere. And the orange here is the overlap between the BCS S-wave model and the exact ground state for this many electrons on a sphere. And you see it's like up to 97% at its worst here. This overlap works all the way from small to large separations. The overlap works well. And of course, the Hilbert space is something like, I don't know, 1,000 different states with L equals 0 here. So this 97% overlap is pretty darn good. The green is this blue here, the P wave. You can't see it. It's really completely hidden, almost completely hidden. There's really no difference between what you find for the BCS and for the P wave and S wave trial waveforms. They're not identical, but they're very close together. And probably, if it's done right, they're really trying to describe the same state. And on the other hand, here's what you would see if you have the CFL. This is just independent composite fermions in the 2 layers, and you see that works well at large separations, but it doesn't work well at small separations. The correlations are important, and eventually this is not. And this is the 1-1-1 state, which was talked about, which is exact in the SU2 limit, where there's no separation. And then this doesn't work so well at larger values of D over L. And now you can say, well, we've fit this to some kind of BCS-like state. Let's try to extract from it the BCS gap parameter, and we could look at the correlation length. And again, this is from this, what the fit for 6 electrons, 12 electrons on a sphere. This is the rate. You can't really, we're not measuring delta and EF separately, but the ratio between them tells us what the occupations of the various states are. And you can see that delta of EF here seems to go to 1 at small separations, and it falls off rapidly at large separations, whereas the coherence length grows actually quite large. It's on a logarithmic scale for large separations. But these are just finite-sized systems, so you have to take it all with a little bit of grain of salt. Here's what actually happens if you try to fit to the BCS form. What we do is we're calculating, this is a wave function, which is occupation numbers in various composite fermion momentum shells in various system sizes, and you try to fit it to a BCS function, which tells you how the occupations N of K should fall off with basically with K divided by L. K over LB is basically the same. KLB is basically the same as K over the Fermi momentum. And you can see that at large separations, the fit predicts that if we went to infinite system sizes, it would fall off very rapidly, sharp, as you would expect for 2 independent Fermi systems. There's some smearing because of the finite size systems effects. But as you get to smaller and smaller D over LB, it gets more and more spread out, and you're starting to mix in states with different occupations. Okay, and I've just showed you what happens for balanced layers. This pairing form also works for unbalanced layers. It's sort of obvious that there's no problem with it. If I have nu1 different from nu2, but the sum is still equal to 1. So let's say nu1 is less than a half. I'm going to put electrons in that layer and holes in the other layer. The number of electrons and holes is still the same, even though the layers are unbalanced. And there's no reason why I can't pair up the electrons and holes, the composite fermion electrons, composite fermion electrons and holes, and the trial wave function works perfectly well. But I should say the P wave case, which is, it's not obvious, but trial wave functions, we haven't worked them out, but they may work reasonably well in that case too. It's just much harder. It's much easier to understand what happens in the unbalanced case if you think about electrons in one layer and holes in the other. Whereas in the P wave case, you have to pair up electrons in both layers, and they don't have equal numbers anymore. The calculations on, again, I emphasize that we see a smooth transition, but we can't rule out the possibility of a sharp phase transition, or the possibility of having various intermediate phases as a separation between D over L increases, because the energy differences between them are very small. And theory doesn't rule it out in the balanced case. I should say in the unbalanced case, then we know that phase transitions must occur, because in particular, if you had say 2/5 and 3/5, then we know at large separations you have an energy gap, and at some point the energy gap disappears and there's a phase transition there. And if it's in between at some arbitrary phase factor, we know that at large separations you should really get phase separations and inhomogeneities, and that should happen. So it's very complicated what will happen at unbalanced systems, but even theoretically we don't know. But again, even at the balanced system, we don't really know what happens. And of course, Jim's experiments tend to point to a rather sharp transition between the paired and unpaired systems happening in his case around D over L equals 1.8, and we don't know if that's fundamental or not. Now let me turn to a somewhat different question, which is what happens at finite temperature. So let's suppose that we have a system which is an exciton superfluid at T equals 0. Let's think about the balanced case for the moment. It doesn't have to be balanced. If it is a superfluid at T equals 0, then it carries, it is a Bose condensate at T equals 0, it carries a counterflow current with no dissipation at T equals 0, at least it should. And then as we raise the temperature, there should be some sharp phase transition at some temperature Tc where the exciton superfluidity disappears. And in principle, for T less than this finite Tc, the counterflow resistance should be exactly 0, at least in the limit of low measuring currents. And what we expect, at least in the tight binding case, is the behavior, or rather generally, we expect that if we get close enough to Tc, the behavior should be of the Kostler-Staulis type, because we're having excitons which are losing their superfluidity. And above Tc, well, many different things, behavior can be different in the two limits. In the BCS-like regime, where the binding is weak, we would expect that rapidly as we go above Tc, you have really independent composite fermions in the layers, and Tc should saturate to some kind of normal resistance, which would be just determined by scattering of the free composite fermions in the two layers, either off each other or off impurities. But it's a little bit less clear what happens in the intermediate region. So now I'd like to, that's what I want to say about theory for the moment. Let me just talk a bit about some measurements that I was involved in, which are still on the archive, were recently put in the archive in December, that were done by Xiaomeng Liu from the Harvard group in collaboration with the Dean group, measuring, in particular, they're focusing on measuring the counterflow resistance, keeping nu total fixed, at nu total equals 1. And let's see if I can get this to work here. So, okay, so this color, so this temperature in this direction, and D over L in this direction. And so you can see that at low temperatures, blue means that there's no counterflow, very little counterflow resistance. It's the condensed phase. At high temperatures, we get some kind of finite resistance and in the counterflow. And at large D over L, where we have this sort of Coulomb, the BCS-like region, we're seeing a rather sharp transition. It's not perfectly sharp, but it's fairly sharp. And it gets much blurrier in the smaller D, smaller magnetic field, the smaller D over L regime. And here you can see a cut along these three curves. So the red cut, you can see it's really quite sharp. The resistance increases quite rapidly, whereas it's much smoother in the green and blue regions. And so you can see that if you plot it on a log versus 1 over t, in the green and blue regions, it kind of fits exponential activation, but this looks quite different. It's rather horizontal, then drops much more rapidly. Now, of course, one complication is that you're working at finite measuring currents, obviously. So if you really want to see how sharp is the transition, it could be affected by the fact that there's finite measuring currents. And what we know, theoretically at least, if you have a Koslitz-Thouless type transition, if you go below the transition at zero current, you should have zero resistance. But at finite currents, you get a finite voltage, which should go not linearly anymore with the current, but as some power of the current, I to some power alpha, and that should start roughly as alpha should start as 3 at the Koslitz-Thouless transition temperature, and should increase as you go below it. And at least qualitatively, that seems to be what's happening here. So we see at least some evidence for seeing a Koslitz-Thouless type transition in this region of large magnetic fields. But as I say, in small magnetic fields, it doesn't seem to work very well. And I think that's also similar to the kind of things that were seen in, that was, I think, reported by Jim Eisenstein and gallium arsenide, that he seemed to see activation, even some dissipation in counterflow, even at very low temperatures. And again, the cause is not clear, whether there's contact effects, whether it's just what the cause is a mystery, and it needs further exploration. And again, this just shows us the way the transition temperature goes in this this is in the large magnetic field region mostly, and you see that we're in a region where that as the separation as the magnetic field gets larger, the transition temperature starts falling, as you would expect, because the D over L gets bigger, so the interaction effectively gets weaker, and so the BCS gap should drop. Okay, so as I said, we don't really understand the activated behavior in weak magnetic fields. Let's see. Okay, I think I have 15 minutes left, so let me just turn to this other subject. Unless there are urgent questions, I could answer those, but or I can take them at the end. Are there some questions that seem really urgent here?
No. So
no, okay.
You can just follow.
Let me go on. So let me talk now about these, again, experiments done in collaboration with some of them are independently done, but with some collaborations in both the Harvard group and the in Phil Kim's group and the Columbia group with Corey Dean. And we're looking here at fractional quantized Hall states in double layers. So again, these are double layers of monolayer graphene separated by two 0.5 nanometers of HBN. Let me just before I say that, let me just return to the nu equals 1 type case, just to answer a question that was posed by Jim, posed to Jim, and he wasn't quite sure. So my understanding is that there are experiments which see the coherent state at filling fraction 3 say in monolayer graphene. It's been seen at total filling fraction 1, -1, and 0. So 0 means you have actually electrons in one layer and holes in the other, and they really do form excitons. And you see the coherent exciton condensate state. In two bilayers separated by an insulator, my recollection is that you do see things at total filling 1. You see something at total filling 3, but not really at total filling 2. And it seems there that, and of course in bilayers you have this degeneracy between the two, the n equals 0 and n equals 1 orbital states. And it looks like that they don't really see condensation when when one or the other layers is in an L equals 1 state, if I recall correctly. At least it's certainly much stronger in the case where they're in L equals 0 states. The L equals 0 states have narrower orbitals, and maybe that's part of the reason. Okay, sorry. So returning to the fractional quantized Hall states. So a quantum Hall state will be, again, a state where the longitudinal resistance vanishes. So both the drive resistance and the drag resistance vanish. And again, there'll be a quantized Hall resistance and a quantized Hall drag resistance. Again, they're quantized in rational multiples of h over e squared, just as in the state Jim was describing. But in this case, the drive layer and drag layer will have different Hall conductances. And again, in his case, as we've sort of indicated, once you're in this coherent state, you can add excitons to one layer or to another layer, and it just changes the energy continuously. There's no gap, and so you can vary the filling fraction in the two layers can be varied. That is, the difference between them can be varied. As long as nu total is equal to 1, you're in a gap. But here, the filling fraction in each layer has a fixed fractional value. It cannot be varied continuously in the absence of localized impurity states. Of course, with localized impurities, you can vary the filling fraction, but the Hall conductance doesn't vanish because you're just varying occupation of localized states. And the references for these experiments are done, they both appeared in Nature in 2019. I'm going to just talk about the Harvard experiments. So the most prominent fractions that were seen have filling fractions 1/4 in each layer, 2/5 in each layer, 3/7 in each layer. It's also been seen with unbalanced situation with 3/13 in one layer, 4/13 in the other, 1/3 and 1/3 in each layer. And there are many additional fractions that were seen by the Columbia group, but let's just concentrate on these. So you can see here, if I look at the drive resistance, again, this is the XY component. The drive resistance is 3 in units of h over e squared, and the drag resistance is 1. Here it's 3/2 and 1. Here it's 5/3 and 2/3. Okay, here, so the drive resistance the two layers are not symmetric, so you get a drive resistance of 3 or 5/2, depending on which layer you're applying the current and measuring the voltage in. Whereas the drag resistance, it doesn't matter. There's actually a theorem that comes from Anzager, which tells you that it doesn't matter which layer you measure the drag resistance, and that one happens to be 1. And then at 1/3, 1/3, we have a drive resistance of 3 and a drag resistance of 0. Okay, so this one, isn't very interesting. It looks like you're just having Laughlin state in each layer, and they're not coupled to each other, so there's no drag resistance. And 3 is exactly what you would get for the Hall resistance in a Laughlin 1/3 state. So we'll forget about that one, but let's look at these, which are not so trivial. And here, this shows you the experimental results. These are the equal filling fractions. the layer filling. So here's 1/2, 1/2. We see a big plateau with, so the red curve. So, okay, so this is the Hall, the longitudinal drag, it vanishes. And the orange and red curve, the red curve is the drive Hall resistance, and here's the drag Hall resistance. So they're equal to 1 h over e squared, as we expect, around nu equals 1/2. But here you see a plateau at the 2/5 state. We get 1 5/3, as I said, 2/3 and 5/3 at 3/7, and at 1/3 we have basically uncoupled layers. Okay, so a theoretical approach, the simplest thing is to, what you do is, can you use a composite fermion picture with different Chern-Simons gauge fields for the electrons in the same layer and in the opposite layers. So we're basically, what we're going to want to do to understand these systems is attach 2 flux quanta for electrons in the same layer, but only 1 flux quanta of Chern-Simons field for electrons in opposite layer. That means that the Chern-Simons magnetic field seen by an electron or composite fermion in layer A is twice the density of composite fermions or electrons in composite fermions in layer A, plus 1 times the density in layer B when measured in units of the magnetic flux quantum, and the reverse for the Chern-Simons field in magnetic in layer B. And now, of course, what we want to do is combine these Chern-Simons fields with the external magnetic field, so we get an external effective magnetic field seen by particles in layer A would be the applied magnetic field minus the Chern-Simons field in layer A, and similarly for B. And we can define filling fractions for the electrons in composite fermions analogous to the single layers. So the true filling fraction is for layer A would be the density in layer A divided by the density of flux quanta in B. And we define an effective filling fraction, which is the density in layer A divided by the effective magnetic field seen in layer A. And these are related by some algebra. It's a little more complicated than the single layer case if PA and PB are different. But if PA and PB are equal, it turns out that you get a simple result that the filling fractions, the real filling fractions, are related to PA over 3A plus 3PA plus 1. In the single layer, it was 2PA plus 1, so you only got odd denominators, but here we can get even denominators as well. If PA and P are integers, then, of course, again, the Fermi level is in an energy gap for the mean field theory, so we would expect, with some hand waving, to find a quantized Hall state, or we might find a quantized Hall state with fractional fillings in the 2 layers that will be given by this formula. And indeed, if we plug that in, we get the answers here for 1/4, 1/4. We have filling fractions PA and PB equals 1. We get for 2/5, 2/5. Let me forget about the transport for the moment, but you get -2, -2 for 3/13, 4/13. We get 1 and 2. Let me skip 3/7 for the moment. Now, what about the transport properties? So transport properties, we do the same thing we did before. So if you have non-zero currents, they're going to generate Chern-Simons electric fields, and you have to apply them, add them to the applied electric fields, and you add a self-consistent mean field theory, which is basically an RPA. The composite fermions respond as non-interacting fermions to effective electric field in the presence of a composite magnetic field. You have to add the resistivity tensors, as we discussed before, according to the Jaffe-Regel rule. So we have the composite fermions of these independent composite fermions in the 2 layers in this picture. And then we add it to this Chern-Simons term, which now has both. So the Chern-Simons contribution is always has no dissipation, but it has an XY component, which is different there's one component between the 2 layers. This is a layer index. So it's 2 between the 2 layers and 1 for opposite layers. So we have this, they're basically 4x4 matrices. that we have to add, but they're purely 2x2 matrices if we only consider the XY components. And if we add them, sure enough, we get the right results for these filling fractions, 1/4, 2/5, and 4/13. We get these unequal drive. We get these unequal drive resistances between the drag and drive layers. That comes from the Chern-Simons field, which has unequal contributions. Whoops. But what about 3/7, 3/7? If you put in the formula, in order to get 3/7, 3/7, you have to set PA equals PB equals minus 3/2. Well, 3/2, as far as I know, is not an integer. So something's wrong here. It certainly isn't going to be stable if we neglect interactions between the composite fermions. But now, if we include interactions between the composite fermions, they could become stable. And what we find is it works if we assume that there's an interaction, a pairing interaction between composite fermions and the half-filled. There's obviously one half-filled Landau level in each species. If we take a half-filled Landau level for composite fermion electrons in one species, with composite fermions holes in the half-filled Landau level, the second layer, we can get something which looks like a Bose condensate of composite fermion excitons of these in these partially filled Landau levels, just like we had in the integer quantum Hall state at nu total equals 1. And now we get a new state. And in this case, it differs. We have this condensate of composite fermions, but the composite fermions coupled to Chern-Simons gauge fields. And that means you can't vary the density continuously. The gauge fields locks the density difference to be 0 from the ideal density difference at t equals 0. And similarly, the coupling to Chern-Simons gauge fields mean vortices. They don't have logarithmically diverging energies anymore. They are finite energies, so there's no sharp Clausius-Thouless transition at finite temperature anymore. One would just predict some exponential activation energy. And indeed, we can work out the consequences for transport at 3/7, 3/7. They're the composite fermions, as I said. They're basically a coherent state between the two levels. So that means if I put a composite fermion current in one layer, it generates a composite fermion voltage equal in the other layer, regardless of which layer it's in. So this resistivity for the composite fermions is 1, 1, 1, 1 in terms of layer indices, and the coefficient is 1 over the occupation, 1 over, which is 2 PA for the total occupation. And you put that in, and lo and behold, you get exactly the consequence that the drive XY is 5/3 and the drag XY is 2/3 in agreement with experiments. And if you put in any other kind of pairing, say if you tried to just make BCS pairing between composite fermions in the same layer or in different layers, it wouldn't work. You get the wrong transport. So the nice thing in this case, being able to measure the transport separately, the contact separately, the two layers, gives us a tool to really distinguish what kind of pairing we're getting. And it shows that interactions between composite fermions are not negligible. They're important in this case, unlike what's mostly seen in the single layer cases where they don't seem to be very important. There are also semi-quantized states which we see when, say, one layer is, the PB is fixed at an integer in one layer, but PA is not an integer, it varies continuously in the other layer, and they result in these straight lines in the plane of nu top and nu bottom, at which we get diminished resistances, diminished drag resistances and so forth. I won't have time to go into that, but let me say that they're also very interesting. And so in summary, quantum Hall effects in coupled layers, we can look at the integer coherent state where we've talked about double wells for gallium arsenide and coupled graphene layers. We've introduced a new trial wave function based on S-wave pairing of composite fermion electrons and holes. And we have a new experimental results in monolayer graphene, which give us at least some signs of a costless Thouless transition at finite temperatures. And then we see these new fractionalized quantum Hall states in double monolayer graphene, which include semi-quantized states, fully quantized states, and states which involve condensate, exciton condensate of composite fermions. And let's say these is just a picture. These are the collaboration in the graphene experiments. These are the various collaborators at Columbia and Harvard. This is my theoretical collaborators, the two people at Oxford. Glenn Wagner is a student of Steve Simons. Deng Nguyen is at Brown University. Thank you.
Great. Thank you for the talk. We have some questions. So the first question is, in what sense are the S-wave BCS composite fermions and P-wave P plus IP pairing topological equilibrium?
Well, it's not so obvious, but what happens is you think of any property you want to compute, and they wind up being the same. For example, compressibility. That is compressibility in the sense that you can decrease the filling fraction in one layer and increase in the other, and transfer electrons from one layer to the other, which you have to be able to do in this coherent state. And it's obvious that that's not going to cost. It looks like it wouldn't cost any energy in the BCS in the S-wave case, because we're just varying the number of quasi-particle electrons and the number of quasi-particle holes remains fixed. But it's not at all obvious that that's the case in the P-wave case, because in the P-wave case, you're comparing electrons in each state. So you're comparing, what's happening is that as you increase the electrons, if you go to slightly unbalanced, you're going to have, say, more electrons, more quasi-particle electrons in one state and more quasi-particle holes in another state. And what will happen is that you're basically, because of of course, that would certainly be a problem for ordinary BCS pairing, but it's not because you're pairing opposite layers. But what's happening here is because of the Chern-Simons fields, you're developing magnetic fields which are opposite in the two layers. The magnetic field vanishes at zero field because it's half filled, and in one layer it becomes positive, the other layer becomes negative, and you wind up with basically what's happening is at small deviations, you have filling fractions. Let's say you might wind up with, say, P filled Landau levels in the top layer and P+1 filled Landau levels in the bottom layer, because you have different numbers of electrons in them. And what's happening is you can form a pairing state in which you pair a P, an electron in say the Pth Landau level of one with a P plus first Landau level in another. Now those have different angular momenta, but in fact the difference in angular momentum is just what you get from a px plus ipy pairing function. So the pi is, so it manages to give you a pairing, and so that pairing can go through and it can withstand differences in the occupation between the two layers. That's just a hint. You have to look at other properties, and it's not obvious that the two are the same. But again, the other thing that sort of confirms that they look like they really are the same, all the properties we can compute theoretically seem the same, but again, the trial wave functions at finite systems, as you saw, we got really excellent overlap between the trial wave functions, the trial wave functions. What I showed you was overlap between the trial wave functions and the exact diagonalization wave functions for finite size systems, and both of those, the P wave and the S wave, gave essentially equal overlap. So they obviously have to overlap well with each other if they overlap with the exact diagonalization strength. So that's as much as I can say. I don't know of a rigorous statement that they're topologically equivalent.
Okay, thank you. The next question is, how about for bilayers at finite separations at total filling mu equals to 1/2? That is mu equals to 1/4 for each layer. Is it also unstable to BCS pairing?
Okay, so 1/4 in each layer. So I should have specified this more. What I showed you at the let's say if we go back. So here we've seen that in this experiment we see this coupled 1/4 1/4 state, which is not the exciton condensate state at filling 1/4 in each layer. This is done at a particular separation between these experiments were done at a particular separation between the layers. If I went to very small separations between the layers, keeping the densities fixed, I would certainly, or that's very small d over L, I would expect to see the exciton condensate state. I would not see this quantized Hall state. And if I go to very large separations, I would see again, I would see two 1/4 1/4 states. I wouldn't see a quantized Hall state. On the other hand, at 1/3 1/3, I do see, it depends on the filling fraction what happens. And the Columbia group actually has done this. They've studied what happens to these different systems at different separations and different magnetic field strengths. And so they could see transitions between situations, these different situations where, in this case, at these intermediate separations, you understand what's going on by fixing one flux quantum for electrons in different layers and two flux quanta in the same layer. A state of nu equals the nu equal. That's how you get this 1/4 1/4 state. If I want to get two independent layers, I fix there's zero flux quanta that are fixed between the two layers only. And if I at very small d over L, I'm going to look at states where I fix the same number of flux quanta at each layer. So, for example, at electron filling fraction 2/5, which would be a total of 4/5, if it were just a single layer with two spin states, the two spin states would be seeing the same Chern-Simons flux, and there would be just two flux quanta attached to each. So all these things depend on distances between the layers.
Great. The next question is 4-flux composite fermion relevant at large layer imbalance? For example, at filling fraction 1/4 plus 3/4. How does that change the ground state at finite d over L?
Well, again, I think what we haven't studied this. So you're talking about total filling 1. And we haven't studied it in detail, but what we would expect is that at small fillings, at small d over L, it goes into this condensed, the BCS, it goes into the BEC condensed exciton phase, and then you don't have to worry about how many flux quanta to fill. If I wanted to really try to understand what happened at 1/4 3/4, I could try attaching 4 flux quanta to the composite fermions in one layer and 4 flux quanta to the composite fermion holes in the other layer, and form a trial wave function. How well that would work, I don't know. Nobody has. In principle, it could work, but we certainly haven't. No one has tried that.
Okay, thank you. So next question: why only 1 flux quanta is added for electrons in opposite layers? Could it be different numbers?
Yeah. So again,
Yeah.
So what I'm saying, these are trial wave functions. You should think about them. And a priori, you don't know what the right answer is. You have to, what you should really be doing here is, for a given Hamiltonian, a given distance, d, a given magnetic field and so forth, a priori, we're going to try all different possible trial wave functions. So we try we calculate the ground state energy in a system which has 1, 2 and 2 in each layer, 2 and 1, 2 and 0, and you could try various other things. And depending on what D over L is, and depending on the strength of the Coulomb interaction and so forth, one or another may win out. And we don't know exactly what the right phase diagram is. It hasn't been worked out in detail. But the important point is that there exists, experimentally, it seems that there exists a range of D over L where the true ground state, the experimentally obtained ground state, is indeed the ground state you would form by attaching 2 flux quanta in one layer, between electrons in one layer and one in the other. But a priori, I couldn't have told you that this was going to work,
Okay.
at least not at this particular filling fraction, not at this particular D over L. I'm not good enough, but someday people will be able to do it.
Mm-hmm. Thank you. So the last question is, not last, one more. So naively, I would have thought that fluctuations of the Chern-Simons gauge field would reduce the lifetime of E composite fermion and H composite fermion, so electron and hole, and that would induce a short lifetime for their bound state. Is there something that I'm missing would stabilize the bound state?
I'm sorry, I didn't quite understand what the question. Let's see.
Yeah. So
let's see. It's written. Wait a minute here. Let me.
You can check the Q&A section.
Yeah, I need to get rid of this. Wait a minute. The lifetime. Okay. Okay, so I think this is referring to the, I think this would be referring to this picture of, say, S-wave Cooper pairing between an electron composite fermion and a whole composite fermion at large distances. And indeed, this could be a problem. What we believe is that with the what we believe is that that indeed gauge fluctuations mean that quasi-particles are not very well defined even as you approach the Fermi surface in that way. And indeed, that's something that the gauge fluctuations could be important. What we would certainly believe is that at a certain point, if the attraction between the composite fermion and the whole becomes big enough to open up an energy gap, then the gauge fluctuations don't destroy that gap anymore. But you're absolutely right that there could be something subtle happening where there's a competition between some kind of depairing effect due to gauge fluctuations and a tendency to form bound states because of the interaction, which we don't know what that interaction is really between composite fermions. It could be that that's true and that that would produce some kind of sharp phase transition between the unpaired state and the paired state. That's certainly possible. And that's what someone should look into that.
Okay, cool. So last two questions. I might have missed this. How do you understand the semi-quantized phase on the trajectory passing through 3/7 plus 3/7, but at their imbalance?
Yeah, so I think one way of understanding what's going on, I didn't talk about it at all, but at 3/7 plus 3/7, if I remember correctly, so if you look at what are the elementary quasi-particles that you can form at 3/7, 3/7. The elementary quasi-particles, which consist of a vortex plus, they're a little complicated, but they have the property that they have total charge 1/7, and it's basically, we say 4/7 in one layer and minus 3/7 in the other layer. Okay, and now if you start adding, if you bias the layers so that they don't want to be equal, and you pass along this line, it becomes favorable to add these quasi-particles. So you're adding quasi-particles that have this, that are unbalanced. So you're changing the balance between the two layers. Each time you add a quasi-particle, you're taking one electron from one layer to the other, but you're also shifting the total occupation by 1/7. And you keep doing that, and that will move you along a line that has slope 3/7 or something like that in the plane. That's what's happening along these lines, that you have one of the two types of quasi-particles is still condensed and has a gap, and the other types of, they're none of them. But the second type of quasi-particle, you're beginning to add them, and they're forming some kind of a liquid. They're not condensing into anything particular necessarily at finite temperatures. It's just some kind of, and they're not pinned. You want to assume that they're weak, that they're not pinned by impurities, so they move around, and that means that what will happen is, if you try to drive one layer, you'll get dissipation. If you try to drive the other layer, it turns out you don't get dissipation. It's a little complicated, but that's what happens.
Yeah. So last question. If one realizes similar mu equals to one state in Moray flat band system, what are the possible ground state? What's the difference from quantum Hall?
Let's see. Yeah, I'm not sure exactly. You're talking about, so generally these Moray systems, there is some tunneling between the layers, but I guess let's suppose we ignore the tunneling. So the extent to which you can separately control the densities in the two layers, I'm not sure. I haven't thought about that. It's a good question. I don't know. But one question would be to whether you can actually separately control the densities.
Okay, cool. So that's all for the questions today. Thank you very much, Bert, for your nice talk. And we can have.
Thank you, everybody.
Yeah, thank you.